When using a modern digital oscilloscope, it is so easy to zoom into a waveform. All you have to do is hit stop and then change the time base. But did you know that this capability has been around since like the 70s? We're going to use my favorite oscilloscope in my collection and take a look at delayed time base, or the origin of zoom and enhance. Wait, not enhance, just zoom on oscilloscopes. First, let's talk about the basic difference between an analog and digital scope. For an analog scope, I have this Tektronix 7704 mainframe system. It has slots for different types of vertical and horizontal modules. By the way, I bought this at a flea market as non-functional. I had to replace a single resistor in the high voltage section to get it to work. Ever since that simple repair, it's worked just fine. Fun fact, this scope is 1 year older than I am. Anyway, its electron gun moves across the screen from left to right. The time per division knob sets how fast it sweeps, and then a voltage at the input deflects the beam vertically to generate a waveform. The trigger condition starts the sweep at the left side of the screen. Now for a digital scope, I'm using the same Multicomp Pro that the Element 14 community sent me for the video on scope form factors. It features a 200 MHz bandwidth with 1 gigasample per second sample rate. Digital scopes draw their screen differently from analog. An analog to digital converter digitizes the analog waveform as dots and then draws a line to connect them. Its trigger circuit tags the sample that meets the trigger condition and then places the trigger point at the center of the screen. Most acquisitions have more points than can be displayed, so that's why you can stop the scope and change the time base to effectively zoom in on part of the previously acquired waveform. Digital scopes almost always have a dedicated zoom capability so that you can see the zoomed in part of the waveform along with the longer capture. But where did this idea come from? It's almost like I'm trying to set us up for something. By the way, I'm using an arbitrary waveform generator to create the square wave that we've been looking at. I put a tiny glitch after the falling edge. Funny enough, even on its display, you cannot see the glitch that's been programmed into the waveform because it is zoomed too far out. And now I get to the flex. This behavior on digital scopes originally came from analog scopes, even though they couldn't store the waveform. They didn't call it zoom, instead they called it a delayed time base. Now, a cool feature of this particular scope is that you can use either of the horizontal modules to set the time base and trigger. So let's start by using the A module and setting it to 20 microseconds per division or 200 microseconds of time on screen. Now we can see the same square waveform that we've seen before. To zoom in, we have to slow down the time base to 1 microsecond per division, just like we did on the digital scope. Well, except here now we have to also mess with the position and intensity knobs to be able to see the waveform. If you've never looked at an analog scope before, you may not realize we've already seen this exact waveform. Look close at the screen's left side. Since we triggered on the falling edge, and the trigger starts the analog scope sweep, we just barely see the edge before the glitch. But that's not the point of this video. That's basically the same thing we did on the digital scope when we stopped it and zoomed in. What I want to do is get that same zoom display on the analog scope. So I went back to 200 microseconds per division and changed the volts per division for the next step. Since we have two time bases, we can put the horizontal mode into Alt, which causes the electron beam to sweep between the A and B time base modules. But because of persistence of vision, we see both waveforms as the scope switches between them. By the way, the intensity difference is because there are separate knobs for each trace, and I forgot to set them to be the same here. Okay, but we haven't gotten to the really cool part yet. The delaying module is called delaying because it can delay how long until the B module triggers. When I enable the delay mode, we see a bright spot on the A or top trace. As I make adjustments to the B trace's time base and delay time, that spot moves around. It is showing us how long the B module waits to trigger and how much time the bottom trace is displaying. In other words, it's like the digital scope and the zoom window. In both of these setups, I triggered on a falling edge to make sure that we saw the glitch. But we can't arm the B module fast enough when using the falling edge, so I need to change the A trigger to be on the waveform's rising edge. On the bottom trace, now we see the falling edge and the glitch relative to a longer sweep. With the delayed time base, we now get the same kind of zoom that digital scopes can do. And you might even understand now why most digital scopes format the screen the way they do when in their zoom or delayed mode. While this feature is useful and cool, it does have a big drawback being on an analog scope. The waveform and the glitch has to be repetitive in order for us to see them because the CRT has to keep getting redrawn. Now later on, analog scopes did start to use digitizers to try to create a stable display. In fact, there's a module for this system that does just that. Unfortunately, I don't have it yet. I will probably never make another video with this old scope, so I hope you don't mind if I point out a few things that I really like about it. First, not only does it have the 4 slots on the front, the entire thing is designed to be taken apart. All of the panels are easily removable. The screen and acquisition units come apart. In fact, that P7001 digitizer module that I mentioned goes right between them. Here's a picture of what that would look like. There's a link to more information in the show notes. On the back, the power supply module not only comes out, but shipped with a cable long enough to remove it from the frame while in operation. Back in 1978, switch mode power supplies were relatively new. And back then, just in general, instruments were made to be much more repairable. Crazy idea, right? I skipped over this in the video, but this scope not only shows the time-based times on screen, but also the delay times. Believe it or not, but this was a super uncommon feature for analog scopes. One of the most powerful features of a digital scope is being able to hit single and get one waveform. But even this 7704 can do that as well. Here I'm going to hit single and, did you see it? Yeah, so that's the problem. A single shot only sweeps the screen one time. So if your time base is fast, you can barely see it. I'll show you one time with the clip slowed down, just in case you missed it. One way the single shot got used was with a camera hood. On one side of the screen are some signal pins that interfaced with some cameras. These attach to the front to block out the ambient light. So it is very likely there are old data sheets which use pictures from a scope just like this one. Early in the video, I mentioned that the digital scope has 200 megahertz of analog bandwidth. One thing that I find hilarious is, so does this one. There's just a slight difference that 40 years can make in terms of size, eh? I hope you enjoyed this look at where a super common digital scope feature came from. Visit the Element 14 community to find show notes with links to the modern tools used in this video, as well as a few things on this scope. Remember, that is the best place to ask me questions because I'm more likely to see them, and I can always answer them there. As always, thank you for watching. For now, it is time for me to get back to vertically deflecting waveforms on my electronics workbench.